So last time I started talking about basically a basic geometric measure theory tools. And so what I ended last time was this formula that is important that let's say if you have this gamma is a C2 surface, C2 k-dimensional surface, then we have this formula that says that the integral for any vector field with compact support, Rn, so that's a vector field. We have this formula that if you divergence but restricts it to the tangent space, if you integrate this, then that's equal to minus of the mean curvature dot G DHK, which I like to put a number 4, where this H gamma is already, we see this is a mean curvature vector. Okay, and so where this divergence is really, so I wrote this last time, but just this means this is, it's really, if you think, well, okay, maybe write this out. So this is Tx gamma, where this, you think this as a projection n by n, this is n by n matrix representing the orthogonal projection Rn to this subspace Tx gamma. So you think this as a matrix, so you just take basically Ij component of this, and then you multiply Gi, Gxj. Oops. So G is, by the way, G is, I'm writing this as G1 to Gn. The vector field. So this is very, you can think this more like a trace of this. If you think this as a matrix, then you have this n by n matrix multiplied by basically nabla of G, which is going to be the n by n matrix, of course. So you compute this matrix product and then take a trace. This would be the divergence. Okay, so this is true for this just nice C2 surface. And now I should add this one thing. By the way, so I want to define this notion of this mean curvature for a less regular surface. And so one thing that I like to think this divergence or the mean curvature is the so-called the last time I introduced this notion of K integral. So when mu is K integral, so that means that there exists this gamma, which I defined as rec K. So rec K means it's a countably K rectifiable and have a locally finite K-dimensional measure, and also, let's say, measurable, HK measurable. And also there exists a theta, which is the natural numbered multiplicity function such that mu is represented as theta times basically HK restricted to gamma. Okay, so that was a notion I introduced last time. Now for this, I explained this that for this rectifiable set, we have a notion of tangent space almost everywhere. Okay, so this for this gamma, if it is rectifiable, then there exists a notion of approximate tangent space. Okay? This exists for almost everywhere. HK almost everywhere. It's a unique tangent space, okay, for almost everywhere. And so it is reasonable, or actually it's natural to define the tangent space of this this K integral measure. So what I do is for this mu, which is K integral, I define this Tx of mu to be Tx of mu to be just this tangent space of this gamma. Okay. So again, so you have a K integral, then you have this K rectifiable set, and this guy has almost every tangent space. So I say it's really a matter of notation. Just I call the tangent space of this radon, this K integral measure to be that exact tangent space. Okay, so it's just a notation. Okay, now, okay, so now I want to define the following. Also, you see, we want to talk about of course, the mean curvature flow. So we need a notion of mean curvature, of course. So, so what we do is that the next definition is that it's a little bit quick, but for K integral mu, if they exist exists a mu integrable vector field H, okay, such that this formula folds basically. Such that the this divergence, where the divergence is the one that is restricted to the tangent space of the mu. Okay, this d mu x is equal to minus of h dot g x for all vector field okay. Then I say that H is called the generalized I go with English, US way of writing this generalized mean curvature. Vector. So that's the definition of this quantity. So for of mu. Okay. So let me explain this a bit more. So you see, if this gamma is a C2 surface, this formula it holds for any vector field. Okay. And in fact, any vector field which satisfies this kind of property for any G is actually mean curvature vector. That you can actually characterize the notion of mean curvature vector this way also. Okay? So I use this as a motivation to define a generalized notion of mean curvature vector by asking that H satisfies exactly the same formula, okay, for any vector field G. Okay, so that's so of course if just a remark is if mu happen to be just gamma, okay, where theta is just 1, and also gamma is C2 surface with no boundary. Well, then, of course, the usual mean curvature vector satisfies this condition. So, of course, this generalized mean curvature vector is the usual mean curvature vector, obviously. Okay. So in this case, this this H is nothing but just the usual mean curvature vector. Okay. So, and of course, if the gamma is not C2 surface but has some regularity, you may have this vector field. But it's not that you always have this vector field. Of course, depending on the regularity of the surface, maybe you don't have this vector field. Okay? There may not exist such vector field. Okay, so that is requiring some regularity already to gamma, okay, by asking this. So right, okay. I hope that it's clear. It's really a weak way of defining certain object, yeah, using a test function, basically. In this case, test vector field. Okay, so I hope that's clear. Maybe I put this number. I want to refer to sometimes this quantity, so let's put this 5. Okay, so here is somewhat it's maybe surprising a bit. At least when I first saw it, it was a bit surprising to me. But here's the first sort of non-trivial, highly non-trivial fact is the following. So this is so-called Brakke's perpendicularity theorem. Perpendicularity theorem. And this one is in his book, of Brakke's book. Brakke's. And okay, so I hope this is. I'm not, of course, going to prove this, but I want to use this result. So suppose that k integral mu has generalized mean curvature. By the way, if such things exist, then it's unique. So I write, of course, since it's unique, I write this H to be H of mu. Okay, so because it's unique. Almost everywhere, of course, but yeah, it's unique. So let me write this as H of mu. Then suppose that mean curvature H mu. Then the following holds. Then for mu almost everywhere, X, we have the this property that this H mu at this point X is actually perpendicular to the tangent space of mu. Okay, so this is a claim. So that's very non-trivial. Okay, so I think maybe it's a bit strange looking, but so I should explain this. So note that usually if everything is smooth and nice, mean curvature vector is more or less defined as the principal curvature sum times the unit normal, basically, right? So obviously it's perpendicular by definition because it's just a scalar function times unit normal, basically. It's obvious in that case by definition. But now this generalized notion of mean curvature vector is not defined like that. It's just defined precisely by this property. Okay, that satisfies just this number 5. Okay, so a priori it's not so clear if this H is actually perpendicular to the tangent space. But actually you can prove that is the case. That is, it's at least almost everywhere. It is actually perpendicular, and it's actually very important that you have this integral, actually. That is, this theta is integer. So I should remark that this is true this holds for integral, okay, k integral 1 mu, but not for sort of a non-integral measure in some sense. That is, if for the one for the measure, okay, to be precise, for mu is let's say theta hk of gamma, where gamma is actually rectifiable, rect k, but theta is not necessarily integer valued, okay? Not well, okay, real valued, I say, okay, real valued function. Okay. So if it's integer, it's locally more or less constant, okay, almost everywhere in some suitable sense in measure. But if it's real valued, it can be so the theta is like a density of the surface energy. But this density varies from point to point, then actually this mean curvature is not going to be a perpendicular. It will have some sort of tangential component, because this mean curvature is really like a sort of surface tension of sort. And so okay, anyway, so yeah, if that's the case, then h and also assuming that this mu has some vector field satisfying this number 5, then typically h of mu will not be tangential. Okay. Because somehow the variation of theta produces some tangential variation of sort. Okay. So anyway, but we are talking about the mostly integral k integral measure. So we use this property, okay, freely, basically. Yes, please. Well, okay, so I should be, when theta is sort of a function which takes not necessarily integer value, but okay, it's if theta has a let's see, yeah, if theta is not just integer valued, but if you have basically this okay, how do I say it? No, yeah, if it's constant, that's fine. Yeah, it's just that when you have a derivative of theta being more like a varying, non-trivial, then yes, yeah. Okay, so I may not be writing this precisely, but I hope I explained this. Okay, yeah. So yeah. So okay, all right. So, but this property is actually very important in many of the computation we are going to see. Yeah. So yeah, and this actually I don't have to assume the existence of general mean curvature, but actually all you need to ask is actually so-called boundedness of the first variation. That's good enough. But in our case, we have usually a better property than that. So anyway, so okay, so that's important property which I use freely. Right. And maybe just for the people who know about this type of things, by the way, so having this property basically tells you that this measure is so-called C2 rectifiable. Okay, so C2 rectifiable. So you have second derivative almost everywhere, actually, in some sense. And that property helps you to have this perpendicularity. Okay, so just for someone. Yeah. Mm-hmm. Hmm? Yeah. Even actually first variation bounded is good enough, in fact. Yeah. So yeah, okay. If I start talking about this, maybe it will become another sort of interesting topic, but we run out of time. So okay, so let me just quickly mention that if k integral mu in, let's say U, in Rn, it's called stationary. Or maybe, I hope that's fine. Stationary. If this generalized mean curvature is equal to 0. Okay, so that's in U. And this is, well, this means that mean curvature is equal to 0, so that means more or less, minimal surface. So stationarity, if it's stationary, I see this as more like a generalized minimal surface or k-dimensional surface in a generalized sense. Okay, so when I say stationary, that means generalized mean curvature is equal to 0. Okay, and some other things. Yeah, finally, I have enough notion to define the Brakke flow. Okay, so Brakke flow requires a bit of a definition. So a family of radon measure, and as I said, you can think this more like a surface measure. Okay, so mu t over some time interval in U, just to localize in Rn, is called, okay, so I should warn that this is not a unique definition, but in my view, this is good enough, is called a Brakke flow. Or maybe you might say generalized mean curvature, generalized mean curvature flow. If the following 4 things is true, okay, you can ask for more if you like, but at least maybe one may require these 4. For almost all time, I ask this mu t to be at least rectifiable, is k integral. Okay. So you see, radon measure can be, sorry, I think family of radon measure. Radon measure can be quite a general object, of course. It can be very rough. I mean, it can be anything, really. But I ask at least that almost all time, not necessarily all time. I want this to be like a surface measure, so I ask this, okay? That's quite natural, I think. Yes. And the B is, well, this is sort of implicitly also assumed. For almost, for any compactly supported time interval and also in domain, I ask that the primum of the measure is mu t of k is finite. So, and in fact, I sort of implicitly assume that the mu t varies at least measurably in time, but and then C, for almost all time, I also ask that mu t has a generalized mean curvature. Mean curvature vector. Okay, h mu t, such that also locally somehow finite. For any k, compactly supported k, and for any I, this I tilde dt, and let's see, k of this h mu t Now this is squared d mu t. This is finite. Okay. So what I'm asking is that for almost all time, this k integral measure has a generalized mean curvature vector. Okay, and it's L2, and this L2 in space time. Okay, so almost all time it's L2 integrable, of course, and yeah. Okay, so this is assumed, and the last is the most perhaps important, but this D is the one that characterizes the normal velocity of this, surface motion, basically. And this is, last time I explained this for a smooth case, but motivated by that smooth case, so here is, this, note that here is positive, so this is positive. And for any T1 and T2, T1, T2, and I assume these things that you saw last time, x and T2, d mu T2 minus u of phi of x T1, d mu T1. This is less than or equal to T1 to T2 and u of nabla phi minus phi h mu t dot h mu t plus phi t d mu t dt. So that's that is satisfying. Okay. So I put this number 7 for this equation. So notice that we saw something like this last time when I was talking about the characterization of the normal speed, right? And I told you that if I think it's, roughly speaking, if you have a nice smooth mean curvature flow, then this inequality is satisfied with equality. Okay? Not necessarily inequality, but even equality. Okay? But here, I'm not asking equality, but inequality only. But as I explained, this inequality was somehow enough to characterize that this surface motion is actually mean curvature flow if everything is smooth. Okay, so just what I just said in the what I said is remark is that well, if you have smooth family, smooth mean curvature flow, gamma t. Then of course mu t, if you set mu t to be equal to hk restricted to gamma t, this is obviously a Brakke flow. Okay. I think it should be clear. Of course, number one, obvious, because it's a smooth surface, so it's K integral. And of course, these are obvious sort of, you have everything up to here. And the only non-trivial thing was this inequality, but we checked that this is satisfied for nice smooth mean curvature flow. Okay, so yeah, so this Brakke flow is really a generalization of this smooth mean curvature flow. Now, so now I haven't explained why we have this inequality last time, and here is a proper place to explain this. But why we have y inequality? Okay, so for this, there's no sort of clear like single reason, but there are at least maybe two reasons. One is the sometimes actually since this is a fairly generalized notion, it is reasonable to expect that some piece of the surface can vanish right away somehow. Okay, so there might be a sudden vanishing, which should be sometimes reasonable. Okay, so the thing is sometimes some portion of surface may vanish. Let's see, for example, yeah, they're very well sort of, well, sometimes it's, so somehow picture explanation would be some kind of flow which may look something like this. Okay? Suppose, by the way, yeah, you have this so-called triple junction. Here, the mean curvature sort of stays finite here. So, and yeah, and maybe I don't explain this for now. But suppose you have some picture like this, then what happens is that since this little guy has a bigger curvature, this shrinks faster than this one. So in finite time, this picture become something like this. Slightly small, it doesn't look so small. But, this can become some picture like this in finite time. So what I'm saying is this guy shrinks faster than this one. So you may have this kind of picture with little, stick, with little line sticking like this. And then at this point, you see, in some sense, at this end point, you have an infinite curvature in some sense. Okay, so you have to know a bit about this computation. But so the point is, only way that you can continue this guy is to sort of immediately erase this line instantly. Then you are left only with this little, pointy things. But you can actually do this can round off right away, and you can continue this flow. Okay, so it's very, so you may actually round off right away and continue. So this line, well, there's no other ways to continue the flow in a reasonable way unless you erase this line right away. Okay, so that kind of things is should be accommodated with this weak notion of solution. So that's one reason. So yeah, that's so if you try to have equality, that's impossible because you cannot erase some portion of the surface if you have equality, okay? Because that happens like instantaneously. Okay? So that's one reason. And the other reason is a bit more technical in the sense that unless you have inequality, quite often it's very hard to show the existence and also compactness also. Okay, so it's not, okay, just some kind of feeding kind of explanation is that you have this quadratic term of h that is, you see minus phi h dot h. Of course, this term is phi h mu t square, okay, with minus sign actually, okay, with minus sign. And when you have this kind of quadratic term, I think if you have worked on the PD problem, I think in some way or another, you always know that if you have quadratic term, quadratic quantity, quite often under the weak convergence, this guy just behaves, lower semi-continuously usually, or well, in this case, upper semi-continuously because minus sign. So that's a sort of the problem. Okay, when you take a limit, you sort of lose this equality. Even if your sequence is actually satisfying this with equality, when you take a limit, because of this term is sort of upper semi-continuous, the limiting guy may have, may jump. Okay? So that's sort of the reason in some sense. unless you have this inequality, it's like you can't have a good compactness property. Okay, so so that's sort of the reason that. Okay, now but because of this inequality, actually the Brakke flow has some sort of serious problem. Okay, so because of this inequality, in fact, this Brakke flow is non-unique, okay, by itself. Because the thing is, whenever you have, suppose, okay, so the reason why, because if mu t is a Brakke flow, and let's say, yeah, t is I, and let's say t0 is any point in I, then you see, because of this inequality, you can always do this. That is, you have something, moving until t0, but at t0, you just let everything to be empty. That's actually is a solution also. So what I'm saying is, just pick any time, and you just redefine mu t to be mu t until t is t0, for example. Now, but you just set this equal to 0, okay, for any time later. That is, well, setting equal to 0 means it's really like you can make, you banish everything, right? At this point, t0. This is a solution in a trivial way because up until this time, this is satisfied. But once you set, at some point, becomes 0, then this term is 0, and this inequality is actually always satisfied trivially. Okay. So because of this property, you can, in some sense, you can always banish and you get a solution. And but this is sort of a trivial non-triviality, non-uniqueness of sort. So there are certain. So what the point is? So Brakke flow itself is not actually, as a definition, is usually not enough. So so this makes this flow more interesting in some way. So one typically needs some supplementary characterization. Additionally, and this could be, this was not so clear until just a few years ago that even it's sort of interesting, but so I think I may not have time to talk about this very much, but you can, we have this sort of, okay, so just maybe I should mention that there's this notion that we came up with that, so canonical Brakke flow. This is paper, I think 23 or 4, I forgot, but this canonical, okay, so that just last year or 2 years ago with Stewart. There's a natural sort of additional, sort of a property that you can add to this notion, at least in the hypersurface case, I guess, yeah. Not for higher codimensional case, but for hypersurface case, there's an additional property that you can ask. And that, so anyway, yeah, this part is still sort of ongoing research topic, I would say. Anyway, so I just want to mention that. But even with this non-uniqueness problem, Brakke flow has an extremely nice property, actually. It's very rich, I would say, in analytically at least. And so that's an aspect that I like to explain. this 2 weeks during this lecture. Okay, yeah. So but before I explain a bit more about this Brakke flow, maybe just a few more terminology. Is that it's definition 6. Out of these usual general Brakke flow, I want to single out one special guy. If for almost all time, if the multiplicity function multiplicity theta of mu t is just equal to 1. Okay, that is, of course, that means mu t is nothing but just hk of some rectifiable set. Then mu is called unit density. Yeah, this theta is, well, it's called multiplicity, but also you can think that as more like a density. So I just say density Brakke flow. Okay, so if you have this form, okay, with no theta, basically, since it's 1, I say it's unit density Brakke flow. Okay, it's just a name. Okay. Okay. Right. So let's see. We got the 45. Yeah. And okay. So before I go into bit more about the property broker, yeah, just one more thing is quick remark is that by the way, yeah, let's see. Let's see. Yeah. By the way, yeah. So if mu is stationary, is k integral, and just stationary, so that is h of mu is equal to 0. Okay, so if mu is just doesn't depend on time, but k integral measure and also stationary, that means mean curvature equals 0, then this mu is this is a Brakke flow, which is independent of time. Mu is time independent Brakke flow. By the way, by obvious reason, all these conditions satisfied, obviously. And then last inequality is also satisfied trivially. The right-hand side become basically h equal to 0. Then you can see that that is satisfied with equality. Okay, just if it doesn't depend on time. Yeah, and if its mean curvature is equal to 0, obvious. Yeah. So stationary k integral guy is actually Brakke flow. So basically, what I'm saying is generalized mean curvature. Generalized minimal surface is a Brakke flow. Okay, that's what I want to say. Yeah, generalized. So generalized minimal surface is a Brakke flow, at least according to this. Okay, so the theory of Brakke flow has to be sort of more like a generalization of the minimal surface theory, of course. Yeah. So whatever you have for stationary or the generalized minimal surface, you sort of hope to prove something for Brakke flow, or vice versa also. Well, I guess if it's true for Brakke flow, then it has to be true for minimal surface also. Okay, that's something that one should keep in mind. And so now for this generalized minimal surface, what's known? Okay, so for this guy, well, let's see. If mu is unit density in particular, so then there's a very nice so-called regularity theory called Allard regularity theorem, which is very important in this field of geometric measure theory. Then the Allard regularity theory theorem, which is 72, shows that basically Allard tells you that this generalized minimal surface is actually smooth, except for measure 0 set. Okay, so it's actually quite smooth. So that there exists a closed set S in the support. When I write SPT, it's support of mu. I hope that's clear what that means. Support of mu is a place mu lives, and such that the support of mu minus S, the singular S is more like a singular set, is a real analytic minimal surface, or k-dimensional surface, of course, and also this singular set has a k-dimensional measure 0. Okay, so in case, okay, so it's a little bit important that it is unit density, but if it's unit density, then Allard regularity theorem tells you that this support of mu, yeah, maybe I should define on these ones. The support of mu means a set of points where mu of already this is 0 for any r. Okay. So yeah, I take this to be, it doesn't matter so much, but maybe I'll take it to be a closed ball. Okay, so support is, you know what that is now. So this support is a nice surface, except for some singularity possibly, yeah. And so you have this for this guy. All right. So now, okay. So that's for stationary case. Okay. So time independent case, but actually we have a very much corresponding theorem for this Brakke flow as well. Very much. So this part I don't think I have time to explain this time, but so this is something that Brakke claimed in his book, but the proof was a bit, or at least very difficult to understand. So I gave a sort of complete proof on this some time ago, almost 10 years ago now. But and also another paper in 14, and also recently we have a improvement. It's yeah, well, okay, maybe I'll just talk about this for later. So suppose mu t is a Brakke flow, but unit density is a unit density Brakke flow. Okay, so you see, unit density is the same as this here. Okay, so it's sort of the same kind of setting. Then for almost all time, there exists a closed set, which depend, of course, on time, st, and also support of ut, such that this k-dimensional measure of this st is equal to 0. And also, any point outside of this st, okay, maybe you can, okay, just maybe for simplicity, maybe I'll just write left for st. There exists some r such that this support of mu s, say, well, okay, maybe it's slightly uncomfortable. Yeah, be r of x over the let's see. So this would be I don't know how to write this, but s between t minus r square and t plus r square maybe is a nice, is a smooth in curvature flow. So what I'm claiming here is that so suppose you have a nice smooth, well, suppose you have a Brakke flow that is precisely the one that I just wrote down, and also assume it's a unit density, then for almost all time there might be a singularity whose dimension whose measure is 0, k-dimensional measure is 0, but outside of that actually it's smooth. Okay? Smooth, and smooth really means a C infinity in space-time. So yeah, smooth is there is C infinity. So it's really this theorem really is a direct analog of Allard regularity theory to Brakke flow, and also there's some other known results, but at least maybe I just state this. Okay. Yeah, let's see. Maybe it's time to erase them. Any questions? I can answer some questions. Yeah, this I think interesting thing about this regularity theory is that this condition seems to be very, yes. This one, yeah, K integral. Yeah. Yeah, exactly, yeah. Yeah. To integral the unit density. Well, if there's if it's not unit density, yeah, it usually for this setting, this having non-unit number makes problem very, very difficult actually. Yeah, even for static case, that is, even in this case of stationary case, actually, unless you have this condition of unit density, it's actually very hard. There is lots of topological, even the topological sort of difficulty that you have to handle. And very little is actually even known for this case. For even time-independent case, actually, is known to be very difficult question. Yeah. So yeah, that's actually some sort of a big question that yeah, people know it's very difficult. Yeah, so I was saying that when I first saw this almost like 30 years ago, I was very struck. I mean, the claim of the Brakke seems like amazing to me because this notion seems to be very weak, with everything, that is even, not equality, but inequality. And I find this result to be very, very curious. And I sort of start investigating on this, and it took quite a while to prove it. So yeah, it turned out, even though this is inequality, it is a very strong restriction somehow that you can impose to this measure. Yeah, a priori, there's almost no, regularity assumption, right? That's just rectifiable. Doesn't really mean much. So. Okay. Yeah, so things that I'd like to talk about for the rest today is some basic property of this Brakke flow. And next time I hope that maybe next time I may not start yet about the existence, but yeah, I define these things, but it's not so clear if such things exist really. So, but it's surprising that there's a very nice, very general existence theorem to this too. Let's see. Yeah, so first about these Brakke flows, very basic property is that so suppose we have a Brakke flow. In U, and then the following is true for F, which is a C2 compact function with a positive non-negative value, and any compactly included interval T tilde. If we set this C to be, this constant to be the supremum of the second derivative of phi at infinity times loop of T is running T tilde of mu T of support of phi. Okay, so that's just a number. Then claim is mu t of phi. Yeah, when I write this, what I mean by this is integral of phi with respect to d mu t. Okay, so when I write this, I think this mu t to be more like a linear function on this continuous function with compact support. So minus ct. This is a monotone decreasing function of time. Okay, so mu t of phi, where phi is just a C2 with compact support, non-negative. This itself may not be decreasing in time, but if you subtract some constant times t, then it will become monotone decreasing function, okay, of time. Easy proof. Just proof is just follow from. So this right, you just look at the right hand side of the inequality 7. Then you note that T1, T2 of dt, and here's u of nabla phi minus phi h mu t dot h mu t. Let's see. So here phi is actually, but note that phi doesn't depend on time now. So we don't have any time derivative of phi. Okay, so you have that. And then, well, you just do a sort of user Cauchy-Schwarz. You have this minus of phi dot h dot h, which is a negative term. Oh, that's a negative term. So just you compute nabla of phi h mu t, you can bound this from above by 1/2 times phi over nabla phi square, and plus 1/2 phi h mu t square. Okay, so you can bound like this, right? Just yeah, just visual inequality. Now we can use this. Well, this part is not so well known, but you can prove that for C2 compactly supported function, the the gradient phi squared divided by phi, this is actually bounded by 2 times the second derivative of phi L infinity. Okay, so you can use this is just a sort of calculus exercise, but you can prove this. So using that, then this you can bound this guy using this one, and you have, of course, this here's a minus phi of h square. So this can be this can be absorbed to this one, and you can make sure that that's using this, then this right hand side of 7, you can prove that this is less than or equal to basically T1 to T2 of C dt. Okay, because this is going to be just you also took this prima with respect to mu t, so yeah, and so this shows basically what I was writing. Okay, so because this is equal to C of T2 minus T1, so and the left-hand side is of course in this case is just phi of x d mu T2 minus phi of x d mu T1. So that shows that this quantity is decreasing in time. Okay, That's all. So in particular, note that this being a monotone decreasing means that this function can jump at most countably many times. It's monotone decreasing. So you can, at least you can't jump infinitely. Well, you can jump infinitely many times, but not uncountably many times, at least. So yeah, you know that this is it's a sort of except for countably many times, it's continuous in particular. So you can actually use this to show that this. So what I was saying was that then mu t of phi minus ct is actually more continuous, except for countably or countable at most. Except for countable set of time. Okay, so you can actually consider a dense subset, the phi j whatever, in C2 compact space. Dense in C compact space, okay, in a Spriemann norm, for example. And I don't go into the detail, but you can actually really show that some density argument shows that in fact the mu t is actually continuous as a measure in time, in t as a Radon measure, except for countable of time. Okay. So and also actually you can actually do the following. That is, you can actually you can also make a sort of a redefine this mu t so that this is actually continuous left. I guess left continuous. I suppose. Yeah. You can actually make this to be a left continuous function too, if you like. I mean, you don't have to do it, but sometimes it's useful to do that. But anyway, so well, at least we know that this measure behaves at least more or less continuously, except for this. There may be a jump, but a jump occurs always downwards in some sense. You cannot jump up. You understand, right? Because it's monotone decreasing. So it can go down, but not up suddenly. Okay. This is a nice property about this. About this Brakke flow. Yeah, if you think about some other surface diffusion, for example, surface diffusion equation that comes from like Cahn-Hilliard, you don't have this property, and that is a serious problem if you don't have this. But yeah, Brakke flow has this very nice property. Very easy to handle. Okay, so yeah, so the next theorem is the first non-trivial property of Brakke flow, very famous. That's called Huskins monotonicity formula. And this is really important for Brakke flow. And without this, it's very difficult to do anything. And in fact, what Brakke didn't have when he was writing a book was precisely this one. When he was writing, it was before 90. So yeah, that was somewhat, I think, this very difficult without having this. So anyway, so what is this? Okay, so for y0 in Rn, any point, any R0. Yeah, well, okay, just now R T is less than T0. One defined a so-called backward heat kernel. Define rho of xt, and which sometimes it's to make the dependence clear. I may write this way also. That is the heat kernel 4 pi T0 minus T over 2 an exponential function of minus x0, x, no, y, yeah, y0 square over 4 T0 minus T. So maybe I should point out it is defined on Rn. It's defined on Rn, but it's not a n-dimensional heat kernel. Okay, but k. So here's a k here. So even though it's defined on Rn, that's k here. Okay, so if it's a n-dimensional heat kernel, then it'll be n, of course. But and so yeah, this guy, if you restrict this function on a k-dimensional plane or k-dimensional subspace, well, in case y0 is equal to 0, then it's like really k-dimensional heat kernel on k-dimensional plane. But yeah, so that's something one has to keep in mind. And then, now under a suitable growth condition at infinity, which we always assume in some sense, condition on mu t of Br as R goes to infinity. So suppose, for example, if this stays finite, that's okay. And for Brakke flow, mu t in Rn, we have the following. So we have for any T1 and any T2 less than T0, Rn integrate this x T2 d mu T2 minus Rn rho of x T1 mu T1. So this is a later time and this is before. Yeah? This is less than or equal to minus of T1 T2 integral of is h mu t x minus plus x minus x y0. Y0, this is perp, I'm going to explain this, but perp of 2t0 minus t square d mu t dt. So that's a claim. That's number, I put the number 8. And here, I had this a little bit mysterious one. X minus x0 perp is nothing but just Tx, so mu t. So you have a tangent space. So it's a more like a normal projection of x minus y0 to the normal projection to the tangent space of this vector. Okay? I write this way. Okay, I hope that's clear. Okay, so I define this rho first. And so this is the weighted sort of, it's a weighted measure mass with respect to this Gaussian at time t2 and minus t1. That is bounded from above by, note that here's a minus here and a quadratic term. So actually it's a, less than equals 0, by the way. Of course, this is, so it is saying that this quantity is monotone decreasing in time. Because this is, right-hand side is less than equals 0. Okay? So this quantity is decreasing in time. And also you know what the rate is here too, and from above, in some sense. Unless this guy is equal to 0, it has to decrease basically. That's a very important quantity. Any question about this? I hope it's clear. Yeah. Sorry. Yes, thank you very much. Yes, thank you. Row of, yeah, thank you. Important. Yes. Okay, so yeah, so I stated this result for the entire space, but you can kind of localize too if you like. Okay, so you can make it into a bounded domain case, but for simplicity, let's look at this case. And that is okay. Any question? By the way, so if you happen to have a stationary, time independent stationary k integral varifold, so that is I erased it already. The case that h equals 0, if you don't have h equals 0 and then it doesn't depend on time, this still is not trivial because I mean this T1 and T2 changes this weight, so actually even if it's stationary or time independent, this is non-trivial actually in this case. No, it's a little bit strange, but because the way this function changes in time, even if disk doesn't change. So yeah, and it's like you probably know, many of you know about this so-called monotonicity formula for stationary varifold, and that is with respect to the disk ball. I mean the monotonicity formula for stationary varifold is usually for ball, but here is somewhat different. It's with respect to this Gaussian weight. So it's a little bit different. I mean, at this point, it's a bit different from sort of a time-independent case, in some sense. Okay, so let's look at the proof. It's actually surprisingly simple. So one very important property that one can check is that for any orthogonal projection matrix, to k-dimensional subspace, which I call it S maybe. S is so S implies this is n by n matrix. Representing projection to subspace S. And I sort of identified the subspace and its projection. So I hope that's not confusing. one can actually show. So if you, I thought that this is a homework. If you want to do it, you can actually prove very easily, just a direct computation, that this equality holds. So this rho yeah, so this plus S perp of nabla rho divided by rho plus nabla rho dt is actually equal to 0, okay, for any s. And so I thought that maybe homework for today is to check this. And you essentially can do this by really, I mean, after all, this is rotational invariant. You know, S rho is rotational invariant too. So you just assume that S is, you know, S is just 1 and 0. And only one here, you know, one here is a K by K matrix here. So you can assume that S is just, you know, a first K plane. Well, yeah, this is identity matrix, this K by K identity matrix, and then the rest is equal to 0. And you just compute with this. Okay? So it's very easy. I hope you understand. I mean, S is just identity matrix here by K. It's really the projection to the first K component, K coordinate. Yeah. And you just compute that, and you compute. So this S perp is actually, the S perp is nothing but just S perp would be just 0, 0, 0. And this part is identity matrix. So this is n minus k matrix. Okay. So you just need to check this identity for this special case, because it's totally rotational invariant expression. Okay, it's an invariant under rotation. So just check with this, and yeah, so that's very easy to do it. Okay, so this surprising equality holds for any s. So that's I put this number 9, I guess. Yeah. Now you just use. Okay, maybe you just use. By the way, let's see. We have until 5. Yeah. Use. Let's see. Use this phi of xt in as a row of xt. Okay, so in inequality 7. Okay. Then just do a little computation. Just a right-hand side of 7 is just a t1 to t2 dt. And let's see. Oh, by the way, so this guy is non-negative. That's fine, non-negative, but doesn't have a compact support, right? We are allowed to plug in only compactly supported function officially, but you can always do a cutoff if you assume that's suitable. So that's why I said here is a suitable growth condition. Okay. So, but the exponential function decays really fast, so you know it's usually not a problem, right? So you have to do some little cutoff argument, but that can be done. And so I'm allowed to use this. So here. To be precise, you have to do a cutoff argument, but let's skip that part, okay, just for simplicity. So let's see. So here is nabla rho minus rho h t dot h mu t plus the time derivative of rho. Okay, so that's the right-hand side of 7. Okay. Now, for almost all time, we know that this mu t is integrable. Sorry, mu t is k integral. Okay, so and also now also mean curvature exists. Mu t exists. And that was part of the property of this Brakke flow. Okay, so we can use the theorem 1, which was this perpendicularity theorem that I told you about. Okay, so here we already use this perpendicularity theorem. So what we can do is, let's forget about time. So using that, just forget about time integral. So we do the following. This h mu t dot h mu t. Okay, just look at this part. You just write like this. So the first you just pull out the minus term. And then you do the following. Just say these strange things. And let's see, 2 minus e. And so I'm looking at this good time, almost everywhere time. So this Navier road dot h, I could add and subtract 1. Okay, so this I'm doing this sort of silly things. But here is by theorem 1, I know that this h is perpendicular to that normal. Okay. Sorry, no, this h is perpendicular to the tangent space. So I could project it to the tangent space. Okay, so this is you can just do this by theorem 1. Okay. I hope that's clear, yeah? I mean, nothing changes if you do this, because we already know it's normal, okay? By theorem 1, almost everywhere. And it's really good, you know, we probably don't know it for everywhere, but we know it's true for almost everywhere, and that's good enough. Okay. We do this, and now we do the following. So you can actually complete the square by subtracting and adding rho square over rho. So see things here. Plus square rho. Okay, so you do you add and subtract this guy, and you can actually complete the square. So this is minus of rho h t minus Navier rho over rho square plus rho Navier rho square and minus Navier rho h. Okay, so that you just did you just completed the square there. Okay. So you see something square term. Okay, so now the rest is just a bit more. Now some other things is that now this guy is well, you can do the following. So let's continue. It's the same. Okay. Now this one, you use the formula 5. 5 is the definition of the mean curvature vector, okay, generalized mean curvature vector. Now look at the number 5. So using 5, you can change this to divergence. Okay, so this you can change this to divergence of Ex mu t of nabla rho. Okay, I mean now nabla rho is like a vector field. Okay, that we had G before. Now G is a nabla rho. Okay, nabla rho is vector, right? So this changes to this. Okay, so now you note that. Okay, so now we have these guys, and also sorry, I think I forgot. Let's see. Okay, we did have this rho t, by the way. Yeah, sorry. Yeah, I forgot to add this one. So yeah, you did have this rho t. So this plus rho t is what we have now. Okay, I hope that's. I hope I didn't mix up. So, you know, this is the right hand side of the inequality 7. I forgot this adding this the number rho t, the time derivative of rho. And I just computed this first part here. So I need to add this rho t at the end. I hope that's clear. And this quantity is actually precisely, in fact, this guy. With, because you see here, divergence of nabla rho is nothing but just Tx mu t. You think this as a matrix, and then you sort of differentiate the second derivative, yeah? Second derivative rho. Now this one, that's what it is. Okay. So if you think this as a projection matrix, it is precisely what you have there, with S being a projection map to the tangent space. Okay, I hope that's clear. You think this as a S, then this is S projected. You know, this is second derivative rho as you see there, and projected to this tangent space and then taking a trace basically. And this term is again the same. It's the S perp of nabla rho here, right? It's actually exactly that one. And so because of that, this just becomes 0. I hope that's fairly clear. Maybe I should write this. See, this is nothing but just Ex mu t projection normal to nabla rho after all. So it's and also mu t is here. So this is exactly the same thing as this. So by using 9, we basically proved it already. Yeah? We proved 8. So that's a proof. Any questions about this? I hope this is fairly clear. You know, it's amazing computation, but you know, it's just after all, it's just a computation. So yeah, the fact that it doesn't matter what kind of plane this is very you know, of course that's the reason that works. Of course, if it can be any projection. So. Yeah, okay, so I hope that was clear. Yeah, okay, so that's a very nice formula because we have this sort of so-called monotonicity of this formula. And let me do a quick corollary of this. Is let's assume mu at the time 0 is finite. So that means really at the initial time, the measure is finite. Okay, total measure is finite. And then, and I'm assuming that it's a Brakke flow in Rn. And then now fix gamma. Then we have the following. Then we have supremum of R, any R, in fact, and the T is bigger than delta square, and X is any point, Rn. Okay, so the supremum of this of mu T of radius R centered at X divided by R to the K. This is bounded by the initial energy or surface times this number, delta K divided by exponential. This number is not so important, but some number depending on delta. Okay, this holds. Okay, so so what this is saying is this quantity is okay. So this quantity, the only okay, T is not close to 0, but at least away from 0 by delta square. So you're looking at slight time. You know, you start with more like images, like you start with T equals 0, and you sort of have to wait a little bit. But once you wait a little bit, then this quantity is uniformly bounded. And this is kind of interesting because, you know, initial surface could be extremely complicated. You know, finite measure doesn't mean it's nice. It can be really ugly, you know, extremely ugly surface with finite measure. But if you wait a little bit, then you have this problem. So that means somehow there's some kind of sort of regularization, which you sort of expect anyway. But but Brakke flow does have this property. I hope that makes sense. I mean, having this bounded means it's really like behaving like k-dimensional surface measure, right? You know, any ball, if you look at the ball radius r, then you know that, you know, k-dimensional measure. The measure inside of the ball radius r is bounded by some constant times r to the k, right? So that means it is somehow behaving like k-dimensional surface measure. But initial data could be like more like a fractal, for example, you know, worst case. And so, you know, if you start out with something like fractal, what happens is sort of very irregular part just kind of vanish right away, in some sense, become very smooth, or yeah, but something is happening. Now, the proof is very easy, but I really don't know I can finish in 5 minutes, but I hope I can do that now. Just fix T, and let's assume that by translation we can assume x equals 0, okay, without loss of generality. Assuming x equals 0, and now consider we want to prove this at the origin. Consider that rho of 0 t plus r square of xt. Okay. So now, so what I mean is y0 is 0, and the t0 is this number. And so here's a t is defined until t plus r square. Yes, yeah. Well, I guess this is obvious. Right. So okay, so just consider that, and yeah, maybe t is not good. I think. Yeah, maybe I should. Yes, it's just different. Then you just use what we proved. So by 8, we with t1 equal to 0 and t2 equal to basically t, y0 equal to 0, and T0 equal T plus R square, okay? So that's how you use it. And then what we have is that in this case, using 8, rho at 0 T plus R square, and X T mu, let's see, Ex is less than or equal to, we have this property, 0 T plus R square and X0 T mu 0. Okay, so I'm using T1 equal to 0 and T2 equal to T, so this is the formula you get. Yeah, it's okay. Is this place closed? I wonder. I think we can stay, yeah. But they're not so happy, I guess. Okay. But is that under 5, was it? Yeah. Okay. But this lecture is supposed to be until 5, is it? Okay. I'll finish it right away soon. Yeah. So, yeah. So the only thing I have to mention is that now you just look at what this is. This left-hand side, you can bound from below. You just write out the inside what that is. Okay. So this is, if you think about this, this is exponential function of minus x squared divided by 4r squared, and 4 pi r squared k over 2 d mu t. So if you write out what this Gaussian is with these parameters, you see, this t1, this minus this become r squared. So you have just only r squared here, and you just restrict this to ball radius r at the origin with the same thing. Over 2, because well, this is after a positive function, so you can restrict it to the ball with radius r, and it's just smaller. And so this is nothing but just dr of 0, and you can actually bound this from like r to the k, and the 4 pi k over 2, and this exponential minus 1 over 4 or something. Okay, so at least you get some constant here. And so that is bounded from below by basically constant times r to the k mu t of dr. Okay, so you can bound the left-hand side from below by this quantity, and from above you can just say that this right-hand side from above, you can bound this by basically, I guess 4 pi. You just drop the exponential part, and t plus r squared of k over 2 d mu 0, which in case t is bigger than delta square, you know that this is at most 4 pi k over 2 delta of k of mu 0 of rk, rm. So that's it. Yeah, basically, that's the end of proof, because you have this, these are constants, and you're bounding from above this quantity. Okay? So that's all. So somehow if you look at the ball radius r, you have a bound on this. Okay, and it's totally uniform. Only from this you can already see that there's some kind of a regularizing effect in some sense. That is, anything which is extremely complicated part will just vanish right away, more or less. Otherwise, this is not going to be true. This is R is for any R, right? So you could be looking at a very small, fine scale, and you know already it's k-dimensional. Okay, so I'm sorry, I think it's almost over. Okay, so see you next Friday. Okay.